let's talk about the equation. Let's put the math behind it here. All right. Put some of the math behind it. I think we've described the orthogonality of it or the normal to it, all that kind of stuff. Let's go ahead and look at the slides. All right. Let me do it this way. Set up slideshow. Okay, play from current slide. I like for it to be here so I can get to the controls here. Okay, here's all we're doing. Coil, you got a coil in here with some magnetic material in there, probably, and then you bring a bar magnet in, changing the magnetic field, pulling it back out. Notice you get a positive 1.2 volts when you're bringing it maximum voltage, then maximum voltage pulling it back out until it goes down to 0 again. And then you just keep back and forth, back and forth, back and forth, and you get a current going. Notice the current runs the opposite way coming in the current than it does when you're pulling it back out. And that's what we learned today in class about, the difference in the current direction and the magnetic field. Well, if the magnetic field is what's happening first that induces the current. Because what we're doing, it's used to generate a current or induces a current. The changing field produces the current. That's the big idea. It's called an induced current. All right? In other words, there's no battery there. Don't plug it into a battery, but what I do is I bring a magnet in there which will make the current change. All right? Here again. Electromagnetic induction, changing the area of the magnetic field. Or, again, so here you go. For each charge within the conductor is moving and experiences magnetic force, F equals QVB. Okay? The separated charges on the ends of the conductor give rise to an motional EMF. Because look what's happening here. I have a circuit. I have a magnetic field that's changing as this thing is moving. I have a magnetic field that's changing. The area is changing. Okay? And if I have a length L here, then that area is changing. What's changing? The dx. What does dx equal? It equals the velocity times the time. Okay? It equals velocity times the time. And so, I take that velocity to the other side, and it gets Q over T, so I get IVB. So VBL, the motional EMF, when I'm pushing a bar magnet along in a circuit like this, the EMF is equal to the velocity times the magnetic field times L. Because I still get, that's the voltage, which remember is equal to the electric field times the distance from the electric field. Well, that starts to get really hairy. Don't worry about it. Just know that this capital E thing is kind of dorky, though. Here's what we're talking about. Saying that capital E motional EMF electromotive force equals a voltage can equal what did they say? I always get because I don't use this one very often. VBL. Okay, in a circuit like this. That's one way to, but the reason that works is because we're changing the area. Because the area is changing delta X over delta T, which gives me my V. Okay. Because the changing area is equal to L times delta X over delta T. That's the reason behind it. So the area is changing. Inside the motional EMF is equal to B. That's staying the same. The area is changing times the cosine of theta. Now notice, when we look at this picture, that's going into the magnetic field is parallel to the normal of this coil. Where's the coil? I'll show you. Here's the coil right here. It's this wire right here that's changing in area. The coil is changing in area. Okay? So that's how that works. The area is L dx dt, and so the changing area over changing time. All right? So if I'm changing the area over the changing time, I'm getting that motional EMF that I talked about earlier. I might have kind of jumped the gun on getting that motion. This is Faraday's law, which is basically the changing magnetic flux. I'm going to say it one more time. Here's the magnetic flux. BA cosine theta. All right? If I change anything in here, usually we change it by rotating. So we're changing the angle. If I change anything by rotating, oh, I forgot to, well, this is the flux. And then the change in flux, or the change in time, and we'll put the number of turns in the wire. That'll equal that EMF. We're getting the same thing with that thing moving here. With this moving here, because we're changing the area. Woo! Beat that horse to death. Suppose the rod is moving with a speed of 5 meters per second, perpendicular to the 8 Tesla that's a pretty big magnetic field. The rod has a length of 1.6 meters and a negligible electrical resistance. The rails also have negligible. The light bulb has a resistance of 96 ohms. Find the EMF produced by the rod and the current in the wire. That is so cool. Because you're going to get that wire to work. So how would that work? It would look like this. What's the information they gave us? .8, so B is equal to 0.8 Teslas. L is equal to 1.6 meters. The resistance in the light, the little bitty bulb there, is 96.0 ohms. And the velocity is 5 meters per second. Wow, they gave us everything we needed, didn't they? So here we go. So the notional EMF would equal V, because there's no in there, because there's only one loop. Okay, it's equal to the speed, which is 5 meters per second, times B, which is 0.8. So we're up to 4. 5 times 0.8 is 4, times 1.6, which would be 6.4. So this is equal to 6.4 volts. All right. So they wanted to know the current in the wire. Well, it's the EMF is equal to I times R. So 6.4 volts divided by 96. That's multiple of 16 too, isn't it? This is 1/4 of 16. No, hell no. It's 1/3 of 16. No. 6.4. I don't know. Oh well. It's 40% of 16. Sorry. I knew it was some even number. So that's 0.4 times 16. Sorry. So it's 0.4 times 16 over 6 times 16. Well, that got us a long ways, didn't it? It's just going to be a dinky ass current. 0.023. Something like that. That's what I think. 0.067. Oh, yeah, because it's going to be 60%. Yeah. 0.067. Multiply my answer by 2. My other answer was right. Done in my head. Not bad. So now, In order to keep the rod moving at a constant velocity, the force in the hand exerts on the rod must balance the magnetic force. Ooh! Oh my goodness! Look at what's going on here. This is so cool. This is so cool. But I think I shortchanged it and didn't give you a lot of problems over this stuff. Now look what happens. Look what happens. This is going up this way, right? You got a current going this way and a magnetic field that's going into the page. So which way is that magnetic force going to go? It's going to go this way. In other words, that magnetic force is going to oppose this motion. You don't get nothing. You don't get something for nothing. In other words, because if it didn't work that way, we wouldn't have a conservation of energy. Because if the force went this way along with the hand, all we'd have to do is get this thing started and we'd have a perpetual motion machine. Can't do that. Well, thermodynamics says no, wrong. And so it's funny how nature made this work. The direction of the force would violate the principle of conservation of energy. Okay. We might talk about this one in class. I'm going to stop here and come back to this one.